Okay, team, in this video we're going to talk about the exciting world of acid chlorides and acid anhydrides. They react very similar. These are the most reactive carboxylic acid derivatives as we learned in the previous video. Okay, so in this video we're going to discuss the reactivity of anhydrides and acid chlorides and how they react with nucleophiles, remembering that we're going to lose these groups as leaving groups, and our nucleophile is now going to become bonded to our carbon-oxygen double bond to give us a new carboxylic acid derivative. So the first thing we got to ask ourselves is, where do these acid chlorides and anhydrides come from? How do we make acid chlorides? The way that we make acid chlorides is very similar to the way that we make alcohols, remembering that back in the day we learned that if you have a primary alcohol, we can treat it with thionylchloride to turn this OH into a good leaving group. One of these chlorides displaces that, and we get an alkyl chloride. So basically the chemistry is analogous, right? What we're doing is we're reacting the OH of our carboxylic acid with thionylchloride to make it from a bad leaving group into a good leaving group. One of these chlorines attacks, displaces that leaving group to go from a carboxylic acid to an acid chloride. The mechanism is somewhat complicated and really not worth learning as far as I can tell. If you want to learn it, that's great, but I'm not going to ask you to know it, nor am I going to talk about it here or in class, but it is in the book. But from this point forward, you should be pretty familiar with these mechanisms because they're very similar to the ones that we talked about in a general sense in the previous video. They're all going to follow a very similar pattern. So what we're going to have is an acid chloride, and it's going to react with some nucleophile, in this case water. And what we're going to lose in each case is a hydrogen, and so now the OH from water becomes the OH of our carboxylic acid. The chlorine is our leaving group, which combined with the hydrogen from water to make hydrochloric acid. What's the mechanism here? Well, let's say we have this relatively straightforward acid chloride. Well, now we're not under acidic or basic conditions, right? So all rules are off. All bets are off. So the mechanism now is that because of the high degree of reactivity of an acid chloride, water, which is generally a pretty crappy nucleophile, can directly attack your acid chloride without activation to give us an intermediate that has both a negative and a positive charge. And to get rid of those charges, this molecule is going to want to kick out that chloride leaving group to give us something like this. Which can then undergo deprotonation by a chloride ion to give the carboxylic acid. So notice that, just like I said before, you have a nucleophilic attack step followed by a leaving group leaving step, but you'd still need to do a proton transfer step to get to your final product. You're always going to have a nucleophilic attack, you're always going to have a leaving group leaving. You might have some proton transfer steps at the beginning or at the end. Okay, so depending on the nature of the nucleophile, we can get different carboxylic acid derivatives. If we have an acid chloride, we can make a carboxylic acid. That's what we did on the previous slide. But what if we don't want a carboxylic acid? What if we want an ester? Well, then what we can do is just react with a different nucleophile. If we have an acid chloride and let's say we use ethanol as our nucleophile, just like before, right? This hydrogen does not show up in the final product, but you do get an O-ethyl, and chlorine is your leaving group. So your result is that you go from an acid chloride to an ester. And the mechanism here is going to be the same as the previous case, but oftentimes what we do is we add pyridine to accelerate the reaction. Pyridine is an amine base, which is capable of removing a proton. So in this reaction, let's see how does this work. Well, we have our acid chloride. We have a good nucleophile, ethanol. The acid chloride is reactive enough that we can attack this thing directly. So we get an O minus here, we get an O, and an H and an ethyl and a plus and a chlorine. And then the pyridine can come along. Since we added pyridine, that can remove this hydrogen to give us O minus, O ethyl, chlorine. And now, when we reform our carbon-oxygen double bond, chlorine leaves and we get our ester. So now what we did was we moved the proton transfer step to before the leaving group leaving step instead of in the previous example. Alright, what if we changed the nucleophile to a nitrogen-containing nucleophile? Well, now it serves two purposes. We use two equivalents of ammonia here. One ammonia is our nucleophile, one ammonia is our base. We're lucky that nitrogen is both nucleophilic enough and basic enough to act as a nucleophile and a base in these reactions. And depending on the kind of nitrogen-containing nucleophile that you use, you can get an amide that looks like this, or with one R group or with two R groups, depending on if you use ammonia or a primary amine or a secondary amine. Tertiary amines, you need to have some hydrogen in there that you can get rid of in that final proton transfer step. Notice that two of the three hydrogens from ammonia are present in the product, one of the two hydrogens in your primary amine, and zero of the one. If you had zero to begin with, you can't make an amide. So let's do a simple example here. Let's say you have this acid chloride. We react with ammonia to make an amide. We're going to directly attack our carbon-oxygen double bond. We're not under acidic or basic conditions. We get an O minus, we get an N with a positive charge and a chlorine, right? We added ammonia, we added excess ammonia, right? So then a second equivalent of ammonia comes along and accepts a proton to neutralize this positive charge. So we get an O minus here, NH2, that's where our hydrogen went, chlorine. Now we can reform our carbon-oxygen double bond to get rid of that negative charge and displace it from the oxygen where it's more unstable to a chlorine where it's more stable, and the net result is that we formed our amide product. Okay. What else can we do with alcohols? Well, we just talked about oxygen-containing nucleophiles. So we had water as a nucleophile, we had an alcohol as a nucleophile, we had an amine as a nucleophile. What if we use a hydrogen-containing nucleophile like lithium aluminum hydride? Now these hydrogens are going to attack the carbon of our carbon-oxygen double bond, and what we're going to get out is a primary alcohol. Right? The mechanism here is that we have lithium aluminum hydride as a nucleophilic source of hydrogen, right? So the hydrogen attacks the carbon-oxygen double bond, and we get our tetrahedral intermediate, right? We get an O minus, and we get a chlorine, and we added a hydrogen to that carbon. Now this carbon-oxygen double bond can reform. We kick out the chlorine, and look what we get as an intermediate. We get an aldehyde, right? We already know aldehydes can be transformed to primary alcohols using lithium aluminum hydride. So the first two steps are our addition and leaving group leaving to give an aldehyde, which then continues to react with their excess lithium aluminum hydride to give our primary alcohol. What if we want to stop it at the aldehyde stage? So if we only want one hydride to react, what we do is we choose a reagent that only has one hydride to begin with, and we use these really sterically bulky groups to prevent it from overreacting. This is called lithium tri-T-butoxy aluminum hydride. Don't worry too much about this reaction. I've never seen anyone actually have the need to transform an acid chloride to an aldehyde. Grignard reagents also can react with acid chlorides. This is also kind of a rare reaction. But for example, let's say we had an acid chloride and we reacted it with methyl magnesium bromide, right? Now we have a carbon-containing nucleophile, attacks our carbon-oxygen double bond. We get an O minus and a methyl and a chlorine. That reforms our carbon-oxygen double bond to give a ketone, which can then react with another equivalent of methyl magnesium bromide to give the ketone where two equivalents. Remember, we said two equivalents of a Grignard react with an ester. Same thing with an acid chloride. That's because there's a ketone intermediate that can react with our Grignard reagent again. So how can we reduce the reactivity of a Grignard reagent? Instead of using magnesium, what you can do is use copper. These species are called cuprates. This is less reactive, so only one methyl group gets transferred. We break our carbon-oxygen double bond, and in a second step it reforms and kick out the chlorine. It stops at the ketone stage. These are two separate steps, so be careful there. It stops at the ketone stage, which is the nice thing about cuprates. Okay, so there's a lot of reactions here, but basically we can distill all this down to make this a little bit simpler, right? Carboxylic acids can be converted to acid chlorides with thionylchloride, and acid chlorides can get hydrolyzed back to carboxylic acids if we use water as a nucleophile. Notice that one of the two hydrogens is gone in the product. If we use an alcohol as a nucleophile, we get an ester. If we use an amine as a nucleophile, we could get different kinds of amides depending on if we use ammonia, primary or secondary amines. Lithium aluminum hydride is a nucleophilic source of hydrogen, so we get primary alcohols. If we increase the steric bulk of our lithium aluminum hydride, we can stop at the aldehyde stage. If we use a Grignard reagent, it's going to add twice 2 carbon nucleophiles to give us a tertiary alcohol. If we reduce the nucleophilicity of our Grignard reagent by using copper instead of magnesium, we can stop it at the ketone stage. There's a lot of reactions of acid chlorides, so you should make note cards for all of these to keep them straight. Next thing we're going to talk about is anhydrides. This is going to be pretty short because anhydrides react exactly the same way as acid chlorides. They're actually a little bit more stable, so most of the time people prefer to use acid chlorides most of the time people prefer to use anhydrides as opposed to acid chlorides. How do you make an anhydride? Well, you just use the salt of a carboxylic acid. So let's say we wanted to make acetic anhydride, we would take acetyl chloride and sodium acetate, right, as our nucleophile. This is going to attack our carbon-oxygen double bond, break that guy. We got an O minus here and a chlorine and our nucleophile. When we reform our double bond, our leaving group leaves and we get our anhydride. Now that we know how to make anhydrides, suffice it to say, anhydrides react exactly the same way as acid chlorides, right? So one way to do this, we just talked about how you make anhydrides. You can hydrolyze anhydrides back to carboxylic acids. You can react them with alcohols to give esters. You can react them with amines in the same way that you can acid chlorides to give amides. You can react it with lithium aluminum hydride to give primary alcohols, sterically bulky aluminum containing reagents to give aldehydes, Grignard reagents to give tertiary alcohols, cuprates to give ketones. These reactions are exactly the same for acid chlorides as they are for anhydrides. So to summarize, you can make acid chlorides from carboxylic acids using thionylchlorides. You need to know how acid chlorides react with different kinds of nucleophiles: water, alcohol, amines, hydrides, cuprates, Grignard reagents. Know that anhydrides are formed from acid chlorides and carboxylate ions. They react identically to acid chlorides, except they're usually a little bit more stable and bench stable, so people prefer to use them generally. Same nucleophiles: water, alcohol, amines, hydrides, cuprates. Acetic anhydride is a very common acylating agent that we'll talk about in class. That's it for this video.